My name is Weiyun Hua. Today, I'm so excited to share my research about recycling geothermal energy from abandoned wells for greenhouses in agriculture. About me, I'm an assistant teaching professor from the Department of Ag and Bioengineering at Penn State University. My research interests focus on natural resources conservation and sustainable agriculture. Well, according to Food and Agriculture Organization of the United Nations, we are facing a big challenge of decreasing agriculture land due to urbanization, global warming, and soil degradation. At the same time, the number of people on Earth is growing fast. By 2050, there could be almost 10 billion people. And with more people, we will need a lot more food, about 70% more than we produce now. So in order to solve this problem, greenhouse is a good solution. So why are greenhouses great? First, they help us grow a lot more food. We can get much higher yields compared to growing outside. And second, they let us grow plants for a longer period. We are not limited by the weather, so we can extend the growing season sometimes all year round. But there is a big challenge. Greenhouses need a lot of energy, a huge amount, specifically 65% to 85% of all the energy a greenhouse uses goes just for heating. This is a massive cost and a big environmental footprint. Therefore, we need clean and cheap energy in agriculture, such as geothermal energy. This map shows us the global distribution of geothermal energy applications in greenhouse management. This map tells us that using geothermal energy in greenhouses is a real thing, and it is happening in many different parts of the world, in the Europe, in Asia, and in South Africa. It shows us the potential of this technology in greenhouses in the US. And we do find a few applications of geothermal energy for greenhouses in the USA, in California, Idaho, New Mexico, Oregon, and Utah. This table shows the geothermal source they used and the geothermal fluid temperature as well as the greenhouse's area. So compared to many other countries, geothermal energy has not been widely used in the USA. Here are some key difficulties for applying geothermal energy for greenhouses in the US. First, the best places for geothermal energy are only in certain area in the USA. And unfortunately, these are not always the same places where we have a lot of greenhouses. And setting up a geothermal system costs a lot of money upfront. You have to drill deep holes, which is expensive and risky. It is a big investment for greenhouse owners, and there is no guarantee it will work perfectly. So this may prevent the greenhouse owners to apply geothermal energy even from trying, especially for those with small and medium-sized business in Pennsylvania. And many greenhouses already use natural gas for heating for a long time because the natural gas is often easy to get. This makes it hard for geothermal to compete, even though geothermal is cleaner in long term. And in addition to that, we don't have a lot of people who specialize in building or fixing geothermal system for greenhouses. Also, it can be tough to find all the special parts and equipment we need for this project. And because greenhouse owners are less familiar with geothermal operations, they are not sure if it's safe and a reliable choice. They worry about the costs, how well the geothermal energy will work, and if it is worth the risk. This uncertainty makes it hard to convince them to switch. So in this study, we'd like to investigate the technical and economic feasibility for direct heat utilization from abandoned well for greenhouses. We'd like to connect the agriculture needs and abandoned resources in Pennsylvania. So the concept we proposed here includes inside the greenhouse. You can see the orange line represents hot water paths buried in the soil. This is where the heat is released, warming the plants and the air inside the greenhouse. After the heat has given off its heat, it cools down, shown in the blue line, and flow back to the surface heat exchanger to pick up more heat. Well, in the geothermal well, we have a closed loop of circulation. The hot fluid shown in right comes up from the deep underground, bring that natural heat, earth heat with it. After giving up its heat, the cooler fluid shown in blue is then sent back down into the earth through the same well to get reheated. So in this map, we can see in Pennsylvania, we have many greenhouses distributed in the Lancaster, Chester, and the Bucks area, southeastern area in Pennsylvania. We also have many greenhouses located in the Boulder, Allegheny, and Indiana in the western area in the PA. These two maps shows the abandoned subsurface infrastructure in Pennsylvania. This map tells us we have a unique opportunity. We have thousands of old abandoned wells and mines. These are already the sources in the ground, deep into earth. On the left-hand side, you can see a map of Pennsylvania with many colored dots. These dots shows the places where old mines have been left behind. The map on the right-hand side shows the abandoned well. As you can see, there are thousands of them, especially in the western and central parts of in the Pennsylvania. They currently pose significant environmental and safety challenges. This but they can also bring up an interesting idea. Can we turn a past problem, these sources, into a future solution for heating our greenhouses with clean, environmental friendly energy? This is what we will explore today. So in this study, we conducted a case study using a campus research facility at Penn State University. This facility consists of 9 greenhouses. Each of them has a 45-meter length, 10-meter width, and 5-meter height. We selected one of them for greenhouse temperature simulation in COMSOL, and we use the 9 greenhouses as a whole for economic analysis. Excuse me. So in this study, when we think about making the geothermal heating system work well for greenhouses, there are some key things we really need to focus on. And here is the objective we have in the study. The first, we'd like to investigate the production temperature from geothermal well at different taps. It tells us how the water or the fluid coming out of the geothermal well actually is. We need it to be hot enough to properly heat the greenhouse. And the second, we like to investigate if the impact of hot water pipe layouts in greenhouse temperature, because we it like how we arrange the heating pipes inside the greenhouse. We need to make sure the pipes are placed in a way that spreads the heat evenly throughout the greenhouse, so all the plants get enough warmth, not just some of them. Third, we like to investigate the impact of circulating water input temperature in greenhouse on greenhouse temperature. This is about the temperature of water that is actually goes into the greenhouse heating pipes. It needs to be the right temperature to keep the greenhouse warm without being too hot or too cold for the plants. And the last one is we like to investigate the economic feasibility by comparing the cost between geothermal heating system and a natural gas heating system. So we like to answer the question and make it clear, does the whole idea make financial sense? Can we build and run this system with an affordable cost for greenhouse owners? Will it save money compared to natural gas heating? We need to ensure it's a smart financial decision in the long run. So first, this is a closed loop geothermal well. We simulate the production temperature from different depths, and this temperature distribution shows the temperature in the rock and in the production well. This figure shows the production temperature quantitatively goes up at the beginning and then decreases over time in a year. The production temperature increases with the increasing depth, as showing black, it's the production temperature at the 3,000 meters, and this is a blue line represents 2,000 meters. So overall, the production temperature can meet the needs of most of the greenhouse for direct use, ranging from 40 to 60 Celsius degree, but it also depends on the area and the crops and needs of the greenhouse. Then we investigate the impact of hot water pipe layouts in greenhouses. We simulated 10 layouts from layout 1 to layout 5. The hot water pipes run along the longitudinal axis of the greenhouses, and with a spacing of 1 meter to 5 meters. From layout 6 to layout 10, the hot water pipe layout are transverse layout. They are perpendicular to the longitudinal axis. Here we compared the temperature profile in greenhouse after 24-hour heating. We compared the layout 1 and layout 6 because they too have the exactly same pipe length in the greenhouse. And in the layout 6, you can see the higher temperature near inlet and the cooler temperature near outlet. As for in layout 1, it provides a more evenly temperature distribution, which is more preferred in greenhouse operation. And then we simulated the different circulating temperature input for greenhouses. These two figures are the average air temperature at 0.5 meter height in greenhouse and the water temperature at pipe layout in greenhouse, respectively. So, for example, if the input temperature is 40 Celsius degree, shown in black, the greenhouse temperature increased to 12.7 after 24-hour heating. The pipe outlet was 22.9. This simulation is based on the January condition, which the average ambient temperature is -3, -4 Celsius degree, which has the coldest average temperature in a year. So we can see the 12.7 is not enough for a greenhouse operation. It has to be like 17 to 20 around for normally for all the for most of the crops. So when the temperature input is 60 Celsius degree, the greenhouse can increase to 20.1, which is a good condition for the crop. That means 60 Celsius degree is needed in January, but in the following months, maybe in May, the temperature don't need to be as high as 60. Then we investigate the economic analysis using the night greenhouse as a case study. We compared the cost for two heating systems. In the geothermal heating system, because the geothermal energy is used from existing well and the energy is free. So the initial investment only includes the hot water pumps in the greenhouse and the heat exchanger. The operation cost in a year includes the electric power consumption for pumps. In the natural gas heating system, the initial investment includes heaters and fans for ventilation and tanks for natural gas storage. The operation cost include the electric powers for heaters and fans and the natural gas for heaters. So the overview of the system specification as shown here, it briefly tells us about the scale and the key numbers we assumed for the economic analysis in the study, such as how deep should we go, how hot is the geothermal fluid, the size of the wellbore, and the size of taps used in greenhouses. This slide shows the calculation we made for the cost for geothermal heating system, including the pumps, cost for pump electric power, and the cost for heat exchanger and the PAP in greenhouses. Then we calculate the cost for natural gas heating system, which generating the same energy as the geothermal heating system. The cost include natural gas cost, total initial equipment cost for heaters, fans, and natural gas tanks, and the cost for total electric for heaters and fans. Then we summarize all the cost here in this table, including initial cost, operation cost per year, and annual maintenance. So the lifespan is assumed at least 10 years for two heating system, and for the annual maintenance, which is 5% of the initial cost. So we can see from the table, geothermal heating system cost for initial cost is around 118,000, while the natural gas is a little bit lower, like 84,000. So in the first 10 years, geothermal looks more expensive by about 33,000. Each year, the operation cost to run the geothermal system is only about $2,000 per year, but for the natural gas heating system, it's much higher at 39,000. This means we save a huge $33,000 every single year on just the running cost with geothermal. So even with the higher initial cost spread over 10 years and a slightly higher maintenance cost, the massive saving in a year operation cost mean that overall, the geothermal heating system for our night greenhouses could lead to a total annual saving of $32,000. This shows that, well, the initial cost investment is for geothermal is larger. The long-term saving, especially on energy bills, make it a very smart financial choice. It is a clear path to save a lot of money over time, while also being a much cleaner heat method, reduce the potential problem like global warming. So you may mention that you may notice that some costs like geothermal wells pump investment maintenance and replacement, well-borne and PAP maintenance, monitoring cost, and the cost of greenhouse development are not included in our calculation because there are some fundings from federal government may able to cover all of them, including the AMLER program and the Pennsylvania Seasonal High Eternal Initiative. The NGO and industry may also helpful to cover some of the cost as well. So here we're going to conclude our research, and in this study, a concept based on repurposing abandoned geothermal well for greenhouses was proposed, and the production temperature, circulating water temperature, and the hot water pipe layout were investigated. We also compared the cost between the geothermal heating system and the natural gas heating system for 9 greenhouses as a case study. So for the future research, we'd like to investigate an idea of optimized coordination of multiple well operation. So like if we use more than one well for a large greenhouse complex, how do we make them work together in the best possibility way to get the most heat? We also, so for example, some of the well can work and some of the well can recover at the same time to generate the more energy if we need. We'd also want to investigate a highly efficient and flexible heating method. This means looking at the different heating method inside the greenhouse. It's whether it's underground pipe heating, under the bench where the plant sits, or even near the roof, and using fans to move the warm air around in the greenhouse. This is a 3 mainly applied heating method in greenhouses nowadays. So this could help us to make the simulation could help us to make the heating more effective and adaptable in the future. And we would also like to dive into the return on investment ROI for geothermal heating. Really looking at the benefits, not just the saving on the energy bills, but also how much more food can we grow within a stable, warm environment, so like the enhanced crop yield, and how much longer can we grow in a year that represents the extended growing season, and all the operation saving we've discussed. So this can help us to put a clear value on all of these benefits could help to make this concept become true in the future. So that's all from me today. I'm so sorry that I can't make it in person today. Here is my email address. If you have any questions or you want to discuss more about details included in this research, please feel free to email me, and I'm be more than happy to talk about my research with you. Thank you so much, and I appreciate it.